Hi guys. So today we will actually look into reaction kinetics. Okay, so we will use this lesson, okay, to do a lesson review, okay, on the reaction kinetics topic and what are the things that we have learned until now. Okay, so we will summarize the entire topic. So the first thing that I want to actually mention is about when it comes to the rate, okay, in our syllabus in CIE. Okay, the rate is defined, okay, the changes in the concentration, okay, divided by the time, okay, per second. Yeah, so it's going to be the time is actually written. Okay, so here I just put time. So the unit for the rate, okay, when we use it later for calculation and so on, is going to be mole dm negative 3 per second. Now, but take note, okay, the rate is not only limited to this. Rate can be also changed in volume of gas per unit time, or it can be also change in concentration divided by time, or it can be other forms of calculation like in terms of electrical conductivity, changes in electrical conductivity per unit time and so on. So this one is just a general for our calculation, so mole per dm cube per second. Yeah, so the reaction kinetics, okay, under this topic, okay, we have learned how to actually measure or methods to measure the rate of reaction. So there are two methods that we have learned. Okay, one is going to be sampling, and another method is going to be the continuous method. Now, for the sampling method, okay, what we need to understand about sampling method, we are going to take a small quantity of sample, okay, at different time intervals. Okay, so I'll just put small quantity of reactants or whatever mixture that we have. Let's say, for example, whatever that we want to measure. Okay, for example, concentration of reactants, or if just any kind of sample, we take the sample while the reaction is actually happening. So we take small quantity of those sample and we do a chemical analysis. Okay, now, so this analysis, since it's not done immediately, because the reaction when you take in a small quantity, the reaction will be still ongoing. So what we need to do is we need to quench the reaction. So this reaction must be slowed down. Okay, it must be slowed down. So normally we use ice to slow them down, and then we do the chemical analysis and we measure, right? But there is also going to be another method, which is going to be while the reaction is ongoing, we do the continuous analysis, right? For example, okay, if we have a reaction that has gas production, so we can actually measure the amount of gas that is being, the volume of gas that is given out, and then we record it according to the time. So we don't actually stop the reaction, or we do not need to quench the solution. Okay, we just do it continuously. So there are some ways, okay, that we can actually do continuous sample. Like for example, you can use gas syringe. Other methods, like for example, if let's say the reaction is producing or involves free moving ions, we can also use the electrical conductivity, okay, to measure the how much changes of electrical conductivity per unit time. So this one we can actually use conductivity meter. We can also use colorimeter. Colorimeter is different than calorimeter. Colorimeter is going to be more to find out the changes of the intensity of the color per unit time. There is going to be another way as well. You can also measure the changes of volume. Okay, so we can actually use dilatometer. So that is going to be another method as well. Okay, to actually measure the changes. Okay, involving rate of reaction, okay, when we do continuous method. Okay, so there is going to be, these are the changes. Okay, these are the changes that we can actually use, okay, to find out related to your continuous reaction. So this you can read. Okay, please read. Okay, very important. Okay, we can actually measure the gas volume, gas pressure. So I'll just have a look so that we don't actually miss anything. Okay, so then, we actually have a look at the way that we actually measure the rate. okay, by using graphs. Okay, so these graphs, okay, we have learned that you need to learn about how to draw tangents and so on. So we will not discuss everything here. I will just summarize it in terms of two graphs over here. So there are two graphs that we need to know, okay, in this chapter. You need to memorize as well. Okay, so this one is going to be the first one is when you measure the concentration per unit time. Okay, so when you look at the concentration per unit time, now assuming that we are talking about reactants, okay, reactants, they can actually decrease, okay, the concentration can decrease over time, or it can also decrease like something like this. Okay, that's going to be another possibilities. There are two types of graph, and plus another one more type of graph where they are going to decrease like this in a straight line. Okay, so maybe until here only. Yeah, so there are going to be two. Yeah, two two types. One is a straight line, another one is going to be curve. The curve is divided into two. So this one, okay, later part we will learn about. Okay, but by now, since we are doing a summary of the topic, so this one, okay, the one that is more steeper, we call it second order reaction. The one that is less steeper is going to be first order reaction, and the one that is actually going to give us a straight line, that's going to be your zero order reaction. But take note, okay, the gradient, okay, the gradient of this graph. So the gradient, normally when we measure, okay, the gradient is going to be, let's say we just take the gradient of this, we draw a tangent, and then we find the gradient. Gradient is y divided by x. The y is going to be concentration, the x is going to be your time. The gradient of this particular graph is going to give you rate of reaction. And from here, what we can see over here is the rate of the reactions for both, okay, first order and second order. Okay, for both of them, the rate, okay, you can see the rate is actually decreasing. Okay, the rate is decreasing. But when it comes to zero order, okay, we can see that the rate is a constant rate because it's a triangle, yeah, all the time. So the constant rate, okay, constant rate, so it doesn't actually change. Okay, so if I want to represent this using another graph, which we definitely need to know, if we change this graph into rate against concentration, so we can see that, okay, if you have this for example zero order, you can see the rate is constant. So the first graph is going to be a constant rate, so it's going to be a constant graph which is going to be zero order. And then when we look at second order, okay, the rate, okay, is going to be, now is going to be something like this. Okay, this one is assuming, this one is assuming, okay, the concentration, when the concentration increases, okay, the rate is going to be in this case is going to increase as well. So you can see the, when I actually draw a triangle, you can see, okay, a tangent, you can see the rate, okay, is going to actually increase, okay, accordingly. So we can see that this is going to be a second order reaction. Now for the first order reaction, the rate is going to follow a straight line, okay, a straight line graph. So this is going to be first order reaction. So please take note, okay, there are three graphs for over here for each of the graph, okay, for each of the graph. So you need to know, but the important thing that we can actually know later part, which is going to be, if you want to identify, okay, which one of this graph, okay, which one of this graph concentration against time, which one is going to be giving us the first order, which one is going to give us the second order. Please take note, first order reaction, okay, when you have this, okay, when you measure, okay, if this one is going to be, for example, 10, okay, if you want to get the half life of it, okay, from 10 to become 5, okay, this is going to be the time. Okay, let's say this is the concentration, this is the time. So the time taken, this is going to be the half life. for the 10, the initial concentration, to become 5, okay, half-life. And you can see from 5, when they become 2.5, okay, if you bring it down, you will notice that the length, okay, of this is the same as the T half over here, okay. And the same thing when you have the 1.25 here, okay. So if you notice that, okay, you have, let's say I just bring it here, if you bring it over here after they have, okay, let me actually draw properly. Okay, let's say they come over here, then I have this. So this is going to be another half-life. If I notice that the half-life is the same, the half-life is constant, okay, then this is going to refer to the first order reaction. Okay, this is going to be for the concentration against time graph. But okay, if you have this graph second order, the graph is going to be slightly steeper. Okay, so it's like something like this. What we notice over here is, let's say this is 10 and I want to get 5. Okay, the half-life is going to be something like this. Okay, let's say this is the half-life. To become 2.5, what we notice over here is, okay, let's say 2.5. You can see that, okay, because we changed the way the curve, okay, is drawn, you can see this is going to be, the half-life is smaller than the previous half-life. So this is going to be another half-life. This is going to be 2.5. So if I actually draw another one, okay, which is going to be at 1.25, 1.25. So I bring over here, you can see that this becomes much more smaller. So it means that your half-life, when you notice the half-life is decreasing, okay, over time, okay, when the time increases, okay, that actually indicates that this is going to be the graph for the concentration against time. That is going to be an indicator of this is going to be a second order reaction. So this is how you actually find out which one is first order, which one is second order. Now for this first order, there is a special formula that we need to remember, okay, where the half-life, okay, can be actually given with this formula T half, this is half-life, 0.693 divided by K, where the K is going to be your reaction constant. Yeah, so that is going to be the reaction rate when you write the rate equation. Okay, so the rate equation, normally when we write, okay, we write rate equals to K whatever A, B, or something like that. This is going to be known as rate constant. Now this rate constant for the first order, for the graph concentration against time, you can use this formula. So this formula only applies for the first order reaction. Okay, you can find out the half-life, and you can also, if you have the half-life, you can also find what is going to be the rate constant. Yeah, so that is going to be the way. Okay, so since we brought this up, okay, the rate, okay, when we actually write down the equation, the rate equals to K A and then B. Okay, if you have M and N, okay, this is going to be the rate equation. So we can actually identify the rate equation only by using experimental data. We cannot actually use the equation, okay, to actually find the M and N. So we have to use experimental data. Okay, so like for example, if let's say if my initial rate, okay, if I have an initial rate and I have the concentration, for example, this is the concentration of A, and then let's say the concentration of A was 1, okay, and then the initial rate was 1. So when it become 2, okay, my initial rate become also 2. Okay, when it becomes 3, my initial rate becomes 3. Why? When I times by 2, Okay, this one also times by 2. 1 times 2 to give you 2. Okay, or when I actually times by 3, this one also change by times by 3. So in this case, okay, the when I write the rate equation is going to be, the rate is going to be first order. Okay, the rate is going to be first order with respect to A. So K first order with respect to A. But if you have, let's say, concentration of B, for example, okay, concentration of B, and then you have initial rate. But now, okay, let's say you have 1, 2, 3, but initial rate was 1. When you double, it's still 1. When you triple, also three, still 1. So you can see when you double times by 2, nothing change. When you times by 3, nothing change. So what does it mean? This is going to be times 2 to the power of 0, which is going to be 1. This one is times 3 to the power of 0, which is going to be times 1. 1 times 1 is 1. So this one, if I write down the rate is K. With respect to B, this is going to be 0 order. B to the power of 0 is always 1. So we can actually just write rate equals to K. That means that B do not take part, or we do not represent them in the rate equation. So there is another one. Let's actually we put another one C, then this is going to be O, for example. Let's actually not confuse anyone with O, maybe P. Okay. So here, okay, let's say we have C, concentration of C, and then we want to actually put the initial rate. Okay, similar. You have three situations. So if you have, let's say, for example, 1, 2, 3, earlier the initial rate was 1. Okay, but when you double, okay, what happens over here? This one become 4. Okay, when you times 3, okay, when you times 2, become 4, times 3, it becomes 9. Now what happens here? This one is going to be times 2, so 2 to the power of 2. It means 1 times 4 is 4. This one times by 3, it means 3 to the power of 2. Okay, it means times what? Okay, so times 9. 1 times 9 is 9. So we can actually find out, say that, okay, that C, the rate is going to be K C to the power of 2. Every single time when you times, okay, is going to be to the power of 2. So that is going to be the second order. So you can see over here, this is going to be first order with respect to A. This is going to be zero order with respect to B. This is going to be second order with respect to C. So if I have all this experimental data and I want to actually write down, I can write down K. The A is going to be 1. So I just put over here. B is going to be 0. No need to put. If you want to put later, we can remove it. Okay, 0. C is going to be to the power of 2. C to the power of 2. So you can rewrite this by writing A, B no need to write, C to the power of 2. This means that B do not have any concentration of B, does not have any impact towards your rate equation. So here, okay, when we say overall order, okay, the overall order for this reaction is going to be, you just look at this 1, this is 2, so 1 plus 2 is going to be 3. We say that this reaction is, the overall order is going to be 3. So this is going to be how we look into the experimental data, okay, and then we try to get the rate equation, okay, or you can also use the graph if it is available to find the rate equation. So let's now focus on the what we call as rate determining step. Now, since we have, okay, uh, rate determining step, okay, sometimes we do have reactions that happen, okay, in multiple steps. Okay, so we need to actually look into those reactions, because if you have, let's say, for example, A plus B plus C to give you D, for example, and they you found out the rate equation, okay, is K, then it's going to be A and then B, for example. Okay, this is actually from the experimental data. You found out the rate is going to be K to the then times A and B, and both of them are first order reaction. So overall order is 2. So if I want to actually write them in multiple steps, and they mentioned that this particular reaction, they actually take part in 2 steps, step 1 and step 2. So take note, one of the step will be a slower step, which is going to be our rate determining step. And step number 2 is going to be your fast step, which is not going to be your rate determining step. Now, under the rate determining step or the slow step, if you have the rate equation giving you the A and B, it means that A and B, let's say we assume that step 1 is the slower step, A and B must be in your slower step. Must. Okay. If you have one mole of let's say for example this is going to be first order and first order, under the rate determining step, which is the slower step, it must be one must be here and one must be here. But I will erase here 1 1. It is understood to give you something. Okay, to give you something. But do remember, okay, we need to actually write down something, okay, that will give you, let's say I give D, for example, to give you D. If I just write like this, okay, I might not be able to get the final equation as A plus B plus C to give you D. So what I will do over here, maybe, okay, I will put, okay, plus, maybe to, I will get D plus AB, for example. Okay, I introduce something new. Yeah. So what happens here in my second step, okay, the C that's supposed to be the reactant, okay, the C should not be inside your slower step, which is going to be your rate determining step. They should not be coming over here. So I need to figure out another equation, okay, to actually find, like for example, to include C over here, okay, but at the same time, I need to eliminate the AB. So how I eliminate AB, I put AB over here, okay, and I am going to get, okay, something, okay, I'm going to get something. So in that case, maybe I will do something like this. I think much more easier if I do like this. Okay, if I put AB alone, okay, AB alone, and AB react with C to give me D. Okay, what is going to happen over here? When I add these two equation, okay, when I add these two equation, I will get A plus B plus C to give me D. The AB, okay, plus AB and plus AB over here, okay, they will cancel. Okay, it means I'm getting back this. Okay, so here I can tell that, okay, this is going to be my slowest step, for example. Yeah, where the important thing is when I have the A and B over there. That is very important. Yeah, so that is going to be how we actually identify the rate determining step. If you want to know more details on this, please actually check the video on the rate determining step. Yeah, so that is going to be the rate determining step. And the last one that we have learned under this lesson, yeah, is going to be related to our catalyst. Okay, under catalyst we have two types of catalyst. Okay, we have homogeneous catalyst and heterogeneous catalyst. Now this homogeneous catalyst and heterogeneous catalyst, they have we need to actually know the how they work. Okay, how they work, and we also need to know some of the examples. Okay, but anyway, the homogeneous catalyst is going to be the catalyst, they are in the same phase with the reaction mixture. Okay, the heterogeneous, okay, I think it's wrong spelling. The heterogeneous catalyst is going to be, they are going to be in the different state or different phase. Okay, the catalyst is going to be in different phase compared to the reaction mixture. Okay, I'll give you some examples. So if you have homogeneous catalyst, okay, and heterogeneous catalyst. Now I will do the homogeneous catalyst first. Okay, there are three equations that I want you to remember, which is going to be ester, okay, plus water to give you carboxylic acid and alcohol. This is going to be hydrolysis reaction, and this hydrolysis reaction happens with the presence of acid. So this is going to be acid hydrolysis. So take note, ester is going to be liquid. This is liquid. This is aqueous. This is going to be liquid, and then this is going to be aqueous. Okay, aqueous or liquid. Okay, it doesn't matter, but again, the state is going to be liquid here. So H plus is also liquid here, aqueous. Okay, it's liquid. So because of that, they are known as homogeneous. Yeah. So second example that I can actually give you is going to be H2O2. Okay, when they decompose, they give you H2O and O2. Okay, what is going to happen is going to be, you are going to use a catalyst which is going to be I minus, and this one is going to be, this is liquid, this is aqueous. So you see same state, yeah, liquid and aqueous. Aqueous is liquid. Okay, it's liquid condition. So this one is going to be gas. Okay, so in this case it's going to be homogeneous catalyst. I minus is a homogeneous catalyst. But please take note, under heterogeneous catalyst, I'll just give you some example. Okay, ammonia production. Okay, this is going to be, to give you ammonium, you are going to use iron catalyst, iron powder. Now this iron powder, all these are going to be in gases, and iron powder is going to be solid, so it's going to be heterogeneous. But the second part, why I want to show you, because the second equation for heterogeneous, okay, they are the same, which is going to be, if you have H2O2, okay, when you decompose to give you water and oxygen. Okay, instead of using homogeneous catalyst, there is also heterogeneous catalyst for this reaction. The heterogeneous catalyst is going to be by using manganese peroxide. Now, manganese peroxide is solid, so the rest is going to be liquid, liquid, and gas. So this one you can see clearly that this is going to be heterogeneous catalyst. Okay, the third one, okay, if you look at the third one, so other reactions when you have perosulfate, okay, per sulfate S2O8 2 minus, okay, when they react with um, when they react with I minus, okay, they are going to change into SO4 2 minus plus I2. The catalyst that is going to be used is going to be Fe3 plus. So if I want to balance this, I think you just balance it this way. Okay, we will actually focus more here in a while. Okay, but if you look at the heterogeneous catalyst, okay, one is going to be, first is going to be ammonia production, and then we also have H2O2. I think the third one you can also have, for example, if you have SO2 plus half O2, one of the contact process, okay, which is going to be, we are going to use vanadium pentaoxide. Vanadium pentaoxide is solid, this one is all gas. Okay, this is going to be another example. Okay, there is another example towards the end also, we learn from the example given in the textbook. Okay, this one is going to be when you use catalytic converters. Okay, when you want to change nitrogen monoxide and carbon monoxide, you can change it into nitrogen gas plus carbon dioxide by using the catalyst rhodium, or you can actually use other catalysts, okay, rhodium, okay, or platinum. Okay, rhodium, okay, rhodium is going to be used, you can change it into this. So this is going to be another way, okay, to show that rhodium is solid, the rest are all in gas. Okay, so this one is going to be used as uh, heterogeneous catalyst as well. Okay, so if you look at here, I think if you try to balance, okay, when I put two here, oxygen, there are if I think I put two there, if I put two there, so I have total four oxygen. For oxygen, I think it's balanced already. Yeah, so this is going to be heterogeneous catalyst. Okay, so let's actually have a look at the homogeneous catalyst, how they work. Okay, so for example 2, okay, if I have H2O2, okay, and then uh, it's reacting with the I minus, the catalyst. Okay, so we actually have a look at what exactly happens. Okay, H2O2, okay, they will react with the I minus, the catalyst itself, to give you IO minus, okay, plus H2O. Now this IO minus will react with H2O2 again, okay, to give you I minus again, okay, plus, okay, H2O. Okay, they will give you I minus H2O. Yeah. Okay, and also I think I forgot O2. Okay, so you can see they are going to be balanced over here. So when we add these two, okay, you are going to actually get this equation. Okay, this is actually what's happening. So in this case, we can see that, okay, the I minus is being used and actually given back. Yeah, so that is the catalyst over here. So we can see that the changes in oxidation number is happening. Okay, so it's actually going to change back again. So oxidation number is involved here. Okay, and then if you look at the third one, okay, the third example. So if you look at the third example, this one is going to be S2O8 2 minus. Okay, when you react with I minus, it gives you I2 plus SO4 2 minus. Okay, this one, okay, if I want to actually represent using equations, okay, what happens is Fe3 plus, okay, because the catalyst is Fe3 plus. Fe3 plus will react with I minus. They will change I to I2 plus Fe2 plus. Okay, that is going to happen first. Okay, please check the oxidation numbers, the numbers here. So the charges, okay, plus 2, this one is going to be plus 2, left and right is all the same. Okay, so this one is going to be, we no need to put the electrons over there. And then when we actually look at okay, the second one, so S2O8 2 minus, okay, S2O8 2 minus, when I change them, okay, when I react, okay, I will react with Fe2 plus. It's going to give you 2SO4 2 minus, okay, and then plus Fe3 plus again, okay. So if you look at the charges here, okay, the charges is going to be, let's actually check the charges, okay. So here, I think Fe3 plus, okay, 3 3 plus, and then plus negative 2, you are going to get plus 1 on your left hand side for the first one. And then here you are going to get plus 2 total. Okay, so what I need to do, I need to actually bring in another electron so that I will balance the charge left and right. Okay, I put electron over there. This is the half-life, half equation. Okay, if you have another half equation, so here I have two negative and then plus 2, that's going to be 0. Okay, 0. And then here is 2 and negative 2 is negative 4, and then I'm going to add with 3, I get negative 1. So I need to bring in another electron here to make it negative 1 left and right, so it's balanced. So when I actually add these two equations together, what is going to happen, the electron and electron will cancel, and I am going to get back the equation, which is this particular equation will be, you will get this equation. So in this case, what is important, okay, I need you to actually understand, okay, what is going to be the reactions that are going to be involved, the two reactions that are going to be involved for these two. Okay, and then the last part, okay, the last part that I want to teach you is about the heterogeneous catalyst. Now the heterogeneous catalyst, the way that they work, okay, you need to remember this term, adsorption. So the adsorb, okay, so the we tell, okay, we tell, okay, that when you have, okay, when you have the catalyst, okay, adsorption, okay, when the catalyst, like for example, if I take it as nitrogen, okay, nitrogen gas, and then I have hydrogen gas. When you have the ion catalyst, for example, okay, so what happened is the gases, they will diffuse, okay, towards the ion catalyst, and then they will adsorb, okay, they will adsorb to the surface of the ion. So they will form bonds, okay, with the iron. Okay, they will form bonds, okay, with the iron. So the hydrogen also, okay, they will absorb, form bonds, and this bond, okay, is a very special bond, okay, where this bond will actually enable some reactions to take place. The reaction that is going to take place is going to be, it will actually weaken the bond between nitrogen and nitrogen, weaken the bond between hydrogen and hydrogen. So what happened is, okay, after the bond is weakened, there will be new bonds that can be formed, and all this happens on this surface of iron. So the nitrogen, okay, they will form the bonds between hydrogen and hydrogen, so they will still stick to the surface of the catalyst. So you still stick to there, okay, there is going to be reaction, so bond breaking and bond formation, but they are still sticking over there. So the last part is going to be desorption. So this option, they are going to actually break the bond from the ion catalyst, so they will actually diffuse out to give you the product. So that is how the catalyst, the heterogeneous catalyst work. They will provide the surface, okay, for the reactions to happen. So earlier diffusion, okay, they will approach the catalyst. Diffusion, where they actually release the products to the from the catalyst, so the catalyst will still be there. Yeah, so this is going to be the entire summary, okay, for the reaction kinetics. I hope that this will really help you to prepare or revise very fast on this chapter. Okay, that's it, guys. Thank you. If you really like the video, okay, you can consider subscribing. You can actually like the video. Yeah, thank you everyone. Bye.